Hi everyone, this is Lab4 Magnetic Field. So the aim was to measure the magnetic field produced by a bar magnet at different distances along and perpendicular to the axis of the bar magnet. After we measured the field at different distances, we compared the measurements to theoretical predictions of a magnetic dipole model. The models and principles shows Biot-Savart law, which is an ideal magnetic dipole, and some key principles is the dipole moment and superposition. System and surroundings. Our system consists of the bar magnet, magnetic field sensor, the surroundings, which includes Earth's magnetic field, the environment, other magnets in the room, laptops, currents from the light, etc. Previews of results. I'm not going to say it. This is what we found. We assume that the bar magnet is modeled as a point magnetic dipole. Distance to observation point is much greater than the length and diameter of the magnet. The magnetic field is only dependent to the magnetic dipole moment and position of vector r. We predicted that, or these are the predictions of our formulas and stuff. The magnetic field magnitude decreases with the cube of distance. On-axis field, along the magnetic axis, the field is twice as strong as perpendicular. The data forms a straight line when plotted. I'll show that later. And the slope is -3 in the natural log. Some of the equations, TLDR, the magnetic field of a bar magnet behaves like a magnetic dipole. On-axis field, perpendicular. We found that the field decreases with the cube of distance, and logs give straight line, slope equals -3. These are the measurements that we found from the different data points. This is 20, 70, 120, 170, 220. That's the distance that we took the measurements from with the phone. These are some of the calculations. And it shows that the magnetic field doesn't drop off as steeply with distance as predicted by the ideal dipole model. Of course, that makes sense because ideal is never going to be accurate because of real world. Some of the code. Because we modeled the magnet and the B fields, we can determine the magnetic field vector at each location in the parallel or perpendicular positions. Green arrows point opposite to the magnets. The red arrow is at a 45-degree angle right here. This represents the experimental location when we're doing the lab. These are some of the calculations that we found. The bar magnet's field does not decay with distance as fast as the ideal theory predicts. In the calculations, the experimental slope is n equals -1.75. It's less negative than the theoretical value. This shows that the magnetic field decay is slower than 1 over r cubed, showing the cause of error was too close to the magnets. Here's some of the figures and diagrams. The two diagrams show how the phone was oriented in order to measure the magnetic field due to the parallel and perpendicular orientations. Excel graph shows the correlations between the data due to the magnetic field and allows for the calculation of mu mag. We can see from the error that we had some experimental errors. This is the apparatus in demo. We used meter stick, magnet, iPhone, and tape. And basically we measured on axis and perpendicular to the axis. And some errors we found was taking measurements too close to the bar magnet. This is an error because the point dipole approximation assumes the value of r is greater than the magnet dimensions. When the measurements are taken at distances comparable to the magnet's length, it can't be treated as dipole moment. iPhone built-in magnetometer may have caused an error. Sensor accuracy decreases for very weak fields, and the magnet wasn't too strong. And we concluded that the experiment successfully demonstrated the magnetic field behavior of a bar magnet and allowed us to test the magnetic dipole moment. Some findings we discovered was we measured B, which is different from the theoretical r cubed. The magnetic moment was 15.3, determined from the y-intercept of our log plot. We found the magnetic field of a bar magnet depends on the direction, and that on-axis field was stronger than perpendicular field, which makes sense. We also found that environmental factors played a big role in the determination of our measurements. In conclusion, this experiment shows the principles of the magnetic dipole fields and the Biot-Savart law applied to a bar magnet.